Well, hello. Today we're going to start Chapter 14, which deals with vector functions. In particular, we're going to do Section 14.1, which deals with vector functions and space curves. Now, first of all, the formal definition of a vector-valued function is a vector-valued function or a vector function is a function whose domain is a set of the real numbers and whose range is a set of vectors. So what a vector-valued function does is it maps the real numbers to either two-dimensional space, or it might actually map it to three-dimensional space. Or if you go into higher mathematics, you actually can have vectors that have more than 3 dimensions, 4, 5, 6, 7 dimensions. All right, but for us, we're going to be looking at functions that map a real number into a two-dimensional vector or into a three-dimensional vector. So as an example, let's just look at this real simple little vector-valued function. F of t is equal to t, comma t squared, comma 3t. Now what this is doing is it's taking a real number t and it's mapping it to this vector. Now I have the vector written in component form, or I could have either written it also as t times I plus t squared times j plus 3t times z. But it's a vector. So if I wanted to evaluate like f of 1, all I do is I take 1 and plug it in for t and get a 1. I plug a 1 and plug it in for t here for t squared and get a 1. And I plug 1 into 3 times t and get 3. So f of 1 is the vector whose components are 1, comma 1, comma 3. F of 2 would give you a vector, and you'd plug 2 in for t here. So you'd get 2, 2 squared is 4, 3 times 2 is 6. Okay, it's that easy. F of negative 1, if I wanted to evaluate it, plug a negative 1 in for t. Negative 1 squared is 1. 3 times a negative 1 is a negative 3. And so what it's mapping is, if you give me a real number, there's a vector associated with it. Okay, and you actually could think of this vector as being a position vector, and this position vector is actually pointing you to the point 1, 1, comma 3, or 2, 4, 6, or negative 1, 1, negative 3. Okay, so this is what a vector-valued function or a vector function does. Now, notice what this particular case, this function f of t, which equals 3t plus 1, comma square root of t minus 5, comma cosine of t, what it's doing is you give me a real number and it's giving me a three-dimensional vector. In order for this t, a real number, to be in the domain of this vector function, the x part, the y part, and the z part all must make sense. This particular function is mapping a subset of the reals into a three-dimensional vector, which we could write as R3. That means a three-dimensional vector. But notice x equals 3t plus 1 must make sense, y equals square root of t minus 5 must make sense, and z equals cosine t. In order for t to be in the domain of this function, all three of these must make sense. So what you're going to be doing is you're going to be taking the intersection of the domain of these three functions that you met back in your Algebra 2 days or Calculus days. So looking at the first function, x equals 3t plus 1, I go, well, gee, that's defined for anything. I can take anything, multiply it by 3, and add 1. So that's all the reals. I look at z equals cosine t. Cosine, you know what cosine looks like. It's going down, up, down, up, down, up. Its domain is all reals. So the only guy that's going to be a problem is this one right here. Y equals square root of t minus 5. And so I go, oh, well, for square root, if I have square root of t minus 5, in order for that to make sense, t minus 5 has to be positive or 0. Or if I add 5 on both sides, t would have to be greater than or equal to 5. So if I drew a little graph of it, it would be all numbers greater than or equal to 5, like that. Or if I want to write this out a little bit more formally, my domain is going to be the interval from 5 to infinity. That's the domain of that function. So again, you have to have the x, the y, and the z components all make sense. So you look at those three functions and you're actually taking the intersection of those three. Let's do another one. Suppose I have the function g of t equals t plus 1 over t minus 2 I plus sine tj plus square root of 3 minus t times k. Well, notice we have x equals t plus 1 over t minus 2. So the domain for that function would be all reals except the number 2, because you can't divide by 0. So this function says, okay, for the domain for g, we have to eliminate 2. 2 is not going to be in that function, in that domain. So if I come down here and just draw a little picture, my domain so far just has an open dot at 2. 2 is not in the mix. All right, now the second function is y equals sine t. The domain for that is all reals. You can take the sine of anything. So I'm not eliminating anything with that, with the y component. The third function is square root of 3 minus t. So that's z equals square root of 3 minus t. Now for that to make sense, what's inside that square root, 3 minus t, has to be greater than or equal to 0, doesn't it? So if I subtract the 3 on both sides, negative t has to be greater than or equal to negative 3, or if I multiply through by negative 1, t has to be less than or equal to a positive 3. So in order for z to make sense, t has to be less than or equal to 3. So far, I eliminated 2, but now I have to be less than or equal to 3. So here's 3. I got to be less than. 2 already got thrown out. So this is what the graph of my domain is for that vector-valued function. For all 3 components to make sense, this is the intersection of those 3 domains. So if I wrote my domain out formally, it would be, let's see, this ray here is going from minus infinity to 2, open parentheses because we're not including 2, union, open parentheses because we're not including 2, to 3, but we are including 3, and that would be my domain. Okay, let's look at another one. Next one that we want to look at, oh, nope, we want to look at a definition. Just like you did limits back in Calc 1, we can do limits in Calc 3. In limits in Calc 3, the definition is very simple. If you have a vector value function r of t whose x, y, and z components are f of t, g of t, and h of t, the definition is so simple. It says the limit as t approaches a of r of t is equal to the limit as t approaches a of f of t, comma, the limit as t approaches a of g of t, comma, the limit as t approaches a of h of t, provided the limits of the component functions exist. So duh, all you're doing is if you have a vector valued function, you're taking the limit as t approaches a, you just take the limit of each of the pieces separately. That's all you do. And if one of those limits does not exist, then the limit for the vector valued function does not exist. All right, so let's look at an example. First one I want to look at is suppose I want to figure out what's the limit as t goes to 0 of sine 5t over t, comma, t squared over e to the t, comma, 3t squared plus 1. So what we have to do is we have to find the limit for each of these individually. So first of all, we're going to figure out what's the limit as t approaches 0 of the x component, sine of 5t over t. Now if you were an A+ student from your Calc 1 days, you might remember that that limit's 5. Okay, if you're struggling a little bit, you might look at it and say, if I plug in 0 into that, the sine of 0 is 0, and t is 0. I've got 0 over 0. I think I'm going to use L'Hopital's rule, and that's fine. L'Hopital's rule, if you remember, says if you have the limit of a function over a function and you've got 0 over 0, as you can see, things that we learned previously we're going to start bringing back. I'm going to have the limit as t goes to 0 of the derivative of the top over the derivative of the bottom, and then find the limit separately. Well, the derivative of sine 5t, the derivative of sine u, is cosine of the angle, but then don't forget, you've got to multiply times the derivative of that angle, which is 5. And derivative of t is 1. And in this case, as t goes to 0, cosine of 0 is 1, so I have 5 times 0, which is 5 times 1, which is 5 on the top, over 1, which gives me 5. So my x component as t is going to 0 is 5. So far I have this limit. The x piece is going to 5. Now unfortunately I have to do it for the y and the z. All right, so we're going to do the y next. We're going to take the limit as t approaches 0 of t squared over e to the t. Okay, t squared over e to the t. Now plugging in for this one, we always try plugging in first, we get 0 over e to the 0. And what does e to the 0 equal? 1. So I have 0 over 1, which is 0. So the y component is going to 0. Okay, and then thirdly, we've got to take the limit as t goes to 0 of the z component. And that one's easy because 3 times 0 is 0 plus 1 is 1. And so the limit for this vector valued function is the vector whose components are 5, 0, and 1. Okay? All right, now the next thing we have to learn how to do is how do you sketch a vector valued function. It's implicit when a function's defined like this that we're sketching it for as t ranges over all the reals. All right, now for this particular one, let's play with it for a second. We're saying the x component is 1 plus t, the y component is 2 plus 3t, and the z component is 5. Does anybody recognize what that graph? We did parametric equations like this before, right? We're saying this is r of t is equal to x plus, so what's happening is this vector is pointing us to a point. You with me? A position vector. And the point, notice if you let t be 0, the point that we're plotting out, if I let t be 0, the point's going to be the point 1, 2, 5. If I let t be 1, the point that my position vector is going to be pointing out is going to be, let's see, t's 1, 1 plus 1 is 2, 2 plus 3 is 5, 5. Who recognizes this? What's this the graph of? What's that a graph of? Do we remember back before when we took our test last chapter? If you had x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct, what was that a graph of? A line. It was the parametric equations of a line that went through, what point did it go through? The point that it went through was x naught, y naught, z naught. That was the point that it went through. And what was this ABC? It was a vector parallel to the line. We don't forget what we already learned, okay? If I have a set of parametric equations, this is the set of parametric equations. So guess what this is? This is x equals x naught plus at. This is in the form of x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. That's exactly what it is. So it's a line. This is the equation of a line. And what's my particular point on the line? My particular point on the line? Well, we let t be 0. As you can see, it's 1, 2, 5. So that's one point that's on the line, 1, 2, 5. And what is our vector parallel to the line? It has components 1, 3, 0. 1, 3, 0. Okay, so I have the line that goes through 1, 2, 5, and the vector that's parallel to the line, the vector that's pointing in my direction, has components 1, 3, 0. Now I'm going to try to draw this, and I'm thinking 1, 2, 5. If I want to plot that point, bear with me. But what I'm doing here, I'm just drawing a little bit of a grid to help me, you know, with sketching my point. If I want to sketch the point 1, 2, 5, I go in the x direction 1, in the y direction 2, and then I go up in the z direction 5. So I'll estimate 1, 2, 3, 4, maybe 5 right here. And that's the point 1, 2, 5. Now notice this vector that's pointing my direction for my line has an x component, it has a y component, but it does not have a z component. The z component is 0. All right, and I want to draw it at that point. Now just to help me, I'm going to put like a line parallel to my y-axis and a line parallel to my z-axis, and I'm just going to draw another little grid just to help me a little bit. This was 1, 2, 5, so I have to have the y be 2. Okay, just to help me with a little bit. Now, if I want to draw the vector emanating from that point that has an x component of 1, I go in starting from that point, I go in the x direction 1 unit, and then in the y direction I'm going a positive 3. 1, 2, 3. And since the z is 0, I don't go up or down. And that vector is pointing me. Now notice I have, what you can picture here is you have a plane parallel to the xy plane. And that vector's in that plane. And we're saying our line starts at this point and it's in this direction. And that line is in the plane that has a height of 5 units above the xy plane. Okay? Now most lines, I picked one that would be easy for me to draw. It's hard to draw a line in three-dimensional space. It's very hard to draw. Okay? All right, let's try to do another one. Oh, I love this one. Put a star by this one. It will be on your test. If we have a quiz next week, it's going to be on your quiz for the day class. All right? It is. Now, let's go back and review just a little bit. Those of you that had me for Calculus 2, we did parametric equations, right? Well, the set of parametric equations that this vector-valued function is satisfying is that my x component is cosine t, my y component is sine t, and my z component is identically 5. All right, now let's go back to Calc 1. If you had a set of parametric equations, and they were in the form of x equals cosine t, y equals sine t. Does anybody remember in parametric equations what that graph looked like? What did that graph look like? It looks like a circle. It's a circle. The reason it's a circle, let's talk. The reason it's a circle is, I think most of us know the trig identity, cosine squared plus sine squared is equal to 1, or sine squared plus cosine squared is equal to 1, right? Well, if x is cosine t, we have x squared here. If y is sine t, we have y squared here. What kind of circle is that? X squared plus y squared equals 1. It's a circle of radius 1 centered where? At the origin. So in 2D, this is going to look like that. It's going to be like a circle. And if you wanted to show the motion, notice if you let t be 0, your x would be cosine 0, your y would be sine 0. Cosine of 0 is 1, sine of 0 is 0. So you'd be at the point 1, 0. Right there you'd be at t equals 0. If you let t be pi over 2, your x would be cosine pi over 2. Your y would be sine pi over 2. Let's see. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. You'd be at the point 0, 1. That's at t equals pi over 2. And you'd be going around like that. You got back to t equals 2 pi. Remember us doing that? Yes, so these by themselves, just in the xy plane, are a circle. It's a circle in the xy plane. Well, the way I like to think about with this one is, since x is cosine t, y equals sine t, remember this is the x plane, this is the x-axis, this is the y-axis, this is the z-axis. What I like to do is I say, oh, just if I were just in the xy plane and I didn't have to worry about that z component, you with me? My x and y is satisfying the equation x squared plus y squared equals 1, which is a circle. So in the xy plane, I'm going to draw the circle whose radius is 1. So if I go, let's just make this go back a little bit and let this go this way. So we're going to go 1, 1, 1, 1. Okay, there's that circle. So the points that are going to be in this, that are going to be pointed out by this vector-valued function, if I did my x and my y coordinate first, I'd always have to be on that circle. But now z, what can z be? Z is always 5. So since z is always 5, what am I doing with that circle? I'm raising it 5 units. So what I'm going to do is I'm going to go up 1, 2, 3, 4, 5. And I'm going to raise my x-axis 5 units. I'm going to raise my z-axis 5 units. 1, 1, 1, 1. And picture, I'm raising that circle 5 units. And so my actual graph for this particular problem is not the guy down here, it's this circle. That's what the vector-valued function, if you let t range from minus infinity to infinity, you'd just be going around that circle a number of times. A lot of times. As t ranges from 0 to 2 pi, you're going to be going around that circle once. And since the height is always 5, we've just raised it 5 units. Okay, now that one's not too bad. Let's change it just a little bit. In this case, my vector-valued equation is r of t is equal to cosine t sine t t. So notice again, we have x equals cosine t, y equals sine t, and we have z equals t. Now again, you should say, oh duh, Mrs. Strocko, since x is cosine t and y equals sine t, I still know that since cosine squared plus sine squared is 1, I have x squared plus y squared is equal to 1. So my x, y coordinates have to satisfy that equation of the circle. So I'm going to draw my circle, x squared plus y squared equals 1, in the xy plane. I'm going to do it in pencil this time. Let's go 1, 1, about 1, about 1. And you guys at home say, well, she's not the best drawer, so I guess I don't get taken off for not being the best drawer either at home, okay? And that's fine. All right, now, notice z can be anything, can't it? So we could go, if I had a point that I'm plotting that's satisfying this equation, since the x and the y have to satisfy the equation of the circle, first when you plot your x and your y coordinate, you're always going to end up being someplace on this circle. But then when you plot z, you're going to be going up some, or you could be going down some. So do we all see that somewhere on this cylinder, this curve is going to lie? Because you're always going to plot the x and the y first, which puts you on the cylinder, and since you could go up z some or down z some, it's going to be somewhere on that cylinder. You all with me on that? Let's plot a few points. Let's just get a handle on what these points are. Now I'm going to rewrite the equation. The equation is r equals cosine t, sine t, and then t. All right, so I'm going to let t be 0. If t is 0, I'm saying, where am I? Oh, let's see. I'm at cosine 0, sine 0, 0, which gives me cosine of 0 is 1, sine of 0 is 0, 0. So I'm going to go in the x direction 1, y direction 0, z direction 0. I'm right there. Let's let t be pi over 2. Now notice pi over 2 is about 1.57. Okay? 1.57. And so I'm going to get my vector cosine pi over 2, sine pi over 2, pi over 2. The last time I looked, cosine of pi over 2 is 0, sine of pi over 2 is 1, and pi over 2 is about 1.57. So I'm going to be, now notice, when I plot my x is 0, my y is 1, where am I? On the circle. But I'm going up z 1.57, about 1.57, about there. So what's happening is, this point, as I'm going from here to here, as x is going from 0 to pi over 2, since the z coordinate is t, it's going to be lifting you up above the xy plane. Let's let t be pi and see what happens. If I let t be pi, notice my vector is cosine pi, sine pi, pi, which gives me cosine of pi is -1, sine of pi is 0, and pi is about 3.14. Okay? So if I plot that point, go in the x direction -1, in the z direction 0, which in the y direction 0, and then go up 3.14. Up 3.14, I'm going to be right about there. Let's try one more. How about t equals 3 pi over 2? I get cosine 3 pi over 2, sine 3 pi over 2, and 3 pi over 2. Somebody on your calculator, do 3 pi over 2 me. What is it, 4.6? Is that what it is? We'll use 4.6 for about. Paul figured it out for me. Cosine of 3 pi over 2, I'm thinking, what does the cosine graph look like? It goes here, 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 here. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is a -1. And 3 pi over 2, what was it, about 4.6? I'll say about 4.6, that'll work. So if I plot the point, go in the x direction 0, in the y direction -1, and then up 4.6 will be about here. And if you notice, what this is doing is, you're wrapping around the cylinder, because your x and your y coordinate is always on that circle, but since the z is t, t keeps getting bigger and bigger and bigger, and you keep lifting it as you wrap around that cylinder. You with me? So it's going to be going up, and it keeps going higher and higher and higher, and you also could make it go down. You see that? Because what's happening is, our equation is cosine t, sine t, t. So the x and the y's are always going to be in that circle, but as t gets bigger and bigger, we're going to be going higher and higher and higher, wrapping around that Campbell's soup can as we go up. I think it would be helpful for us to look at the graph of this on maple. All right, so let's look on maple. Now on maple, what I've done so far, all right, we look so far. What I did already is I loaded with plots, because remember we had to do that the other day. And with plots, notice we have one lovely little thing right here. It's called space curve. All right, now I'm going to make this a little bit bigger so you can see what I'm typing. All right, and my command is, now let's just say, instead of me just saying you what the command is, suppose you're at home or you're doing a maple worksheet and you're going to do a three-dimensional graph and you remember it's space curve. If I forget the name, I type with plots and look at all the commands that I have just opened up, and I see one of the commands right here is space curve. Right there you can see is space curve. If I'm not sure what that command, exactly how you enter that command, if you type question mark and then type and spell it correctly, space curve, and hit enter, you get a little help sheet. And if you look at this little help sheet right here, if you scroll down, I like to scroll down, you will see an example. And I see, first you have to load with plots, which I did. Notice they made it a colon instead of a semicolon. When you do a colon, you don't get the list of all the commands you opened, which is nice because it doesn't take up a whole lot of space. But if you're a novice to maple, it's sort of nice to use a semicolon because then you can see all the different things that you've opened up that you have the capability to do. But as you can see, space curve, it says, the first example, it goes bracket cosine t, comma sine t, comma t, t equals 0, dot, dot, 4 pi. You use brackets in maple when the order that you're listing is very important. When you're giving the coordinates of a point, the x, the y, the z have to be in that order. When you're giving a vector, the x, the y, and the z, the order is important. So you're listing your vector valued function, and then you just tell it what you want t to range from. So if we come back over here, I'm just going to get rid of the question mark, hit end. I'm going to go parentheses, brackets, to name my point. The first is cosine t. Cosine, every trig function, it has to be cosine parentheses. Every function has parentheses on the argument that it's acting on. Sine t, the last one's t, bracket, and we're going to let t range from, now for start with, let's go, we only went 0 to 3 pi over 2 when I was doing it. Let me go 0, dot, dot, 4 times pi. Let me go around the circle twice. Right, and I'm going to hit enter for it to do the graph. Now I suspect since I have it very large, it might be too big for us to see the graph, in which case I might have to minimize. Oh, it looks okay. Now, right now you look at that and you don't have much of a sense, but if I click on it, then up here I have 3 options. I prefer, I mean, you might like the box one around it, or you might like to have the XY axis right inside of it, and you can click on it and you can turn it a little bit, and you see that wonderful spiral. It's a spiral wrapping around the Campbell's soup can, and as t gets larger and larger and larger, you're going higher and higher and higher space. Now, who says t only can be positive? We could have let t go from a negative 4 times pi to 4 pi. And as you can see, if I click on it, put the axes in, and I like to lift it all I'm doing is left clicking and keeping it, the clicker holding down, and rotate it up. I can see this beautiful spiral. It goes forever upward and forever back downward, wrapping around that base, x squared plus y squared equals 1. One of my absolute favorite graphs for vector valued functions, guaranteed. Put a star by it. It is on your test. It will be. Okay? All right. Let's do a different one. Now that we're getting pretty good at this, all right, or maybe hopefully a little bit more comfortable, I look at this one and I say, they want me to describe and sketch the curve defined by r of t equals sine t, comma 4, comma cosine t. Notice x is sine t, y is 4, and z is cosine t. Now in terms of x and z are in terms of sine t and cosine t, so I could say x squared plus z squared is equal to 1, because we know sine squared plus cosine squared is 1. So if I plotted my points, if I did the x and the z coordinates first and then the y coordinate, which I could do, right? The x and z coordinates are on a circle whose radius is 1 and who's centered at the origin. So since this is the x and this is the y and this is the z, all right, I'm going to draw a circle whose radius is 1 in the xz plane. And here's my circle. All right, and granted, you know, we could go through and say, you know, let t be 0, let t be pi over 2, let t be pi, let t be 3 pi over 2. And in fact, if you can see, if I let t be 0, the vector that I'm going to get here is x is sine 0, which is 0, y is 4, and z is cosine of 0, which is 1. So in terms of the x and the z coordinates, we're going to be at x is 0, z is 1, but y is 4. So since y is 4, what are we going to do with this circle? We're going to move it over to this spot right here where y is 4. You see, because the x and the z coordinates are satisfying the circle, but since y is 4, every one of these points is going to get dragged over onto the plane that has y equals 4. So we're taking this circle and we're dragging it over to y equals 4. And this is what our circle looks like. So this is not part of the graph. This was just done to help me. Because since the x, z coordinates satisfy that, all the x, z coordinates would be on that circle. But then since y was 4, every single time you found your x and your z, the y was 4, you had to bring him over. Like this point right here, 0, 4, and then 1. 0, 4, and then 1 starts you right there. Okay? So my circle got moved over. Okay, let's do another one. Oh, this one's sort of cool. This one we have x is t, y is 2t, and z is sine t. Now there's multiple ways that we can do this one, but first of all, let's find out just what equation does the x, if you just did your points on the xy plane and then moved up z, what equation would the xy equation satisfy? Well, notice notice I can't use sine squared plus cosine squared equals 1 this time because I don't have a cosine. All right, so that option's gone. All right, that was cutesy for that one and it's gone. But notice, since y equals 2t, the x and y equations satisfy the equation y equals 2x. You all see that? It satisfies, right, because I just put these guys together. And this gives me y equals 2x. So, let's see. I'm just going to, again, I'm just putting little grids just to help me a little bit in terms of plotting these points and help you to be able to see a little bit better. If I drew the line y equals 2x, when x is 0, y is 0. When x is 1, y is 2. When x is 2, y is 4. You can put one more over here. And the line's going back into the negative part too, but we can just draw it right there. So all of my points that satisfy this vector valued equation are going to be along that line, but they're going to get lifted or lowered according to what your z coordinate is. You with me? When you plot any point that, you know, you let t be 0, t be 1, t be 2, t be pi over 2, anything like that, all the x, y's are going to be satisfying this. So they're going to be along this line. But then since z could be anything, you plot that point, you're going to be going up z. So as you can see, they're going to be somewhere along this plane here that's perpendicular to the xy plane along that line. Now what does z equal? Z equals sine t. Now if I looked at what the x and the y coordinates satisfied in terms of x and z, notice that since x equals t and z equals sine t, in the xz plane, these coordinates would satisfy the equation z equals sine x. Well, what does z equals sine x look like? Z equals, well, y equals sine t, y equals, it's a sine function, right? It's going to be going up and down and up and down and up. So what happens is, if I drag this along here, as you can see, your heights are going to be going up and down and up and down and up. In fact, if we move along this line, if I let's see, why don't we let t be 0? If t is 0, x is 0, y is 0, and z is sine 0, which is 0. We're right here. Now let's let t be, let's try t being pi over 2. Pi over 2 is approximately 1.5. So x is about 1.5, y is about 2 times 1.5, which is about 3, and z is sine of pi over 2, which is 1. So if we're at x is 1.5, y is about 3, z is about 1, and my graph's going to be going up to there. Now why don't we try t equal to pi. X is going to be pi, which is around 3. Y is going to be 2 pi, which is around 6. And z is the sine of pi, which is 0. So if I do 1, 2, 3, 1, 2, 3, 4, 5, 6, I'm down to 0. What do you think it's going to do next? Since your height is the sine of t, I bet you it's going to go up, and then it's going to go down. I should make those dotted because it's below. Then it's going to go up, and then it's going to be going down the xy plane. And this is what your curve looks like. Why don't we put that one on maple so we'll feel a little bit more comfortable? While you're sketching that, I'm going to go back to space curve, and I'm going to let x be t. I'm going to let y be 2t. I'm going to let z be sine of t. Oops, parentheses. And let's tell it to graph it. Whoop, it tells me I'm misiterating an operator. T, 2t, sine 2t. Pardon?
You have to put the star in between.
Oh, thank you. No implicit multiplication. Absolutely. There you go. You know, you look at this and you go, gee, Miss Strocko, I don't see anything there. What are you talking about? Let's click on it. Let's put an axis in, and let's drag it a little bit. It was just the angle that we were looking at had everything lined up. And as you see what the graph is doing, notice if I'm looking down on the xy plane, what does it look like? It looks like the line y equals x, because all y equals 2x. All the x and y coordinates were satisfying the line y equals x. If I look at it in the xy, it looks like the sine curve. And it's going, and that's probably the best way. As you can see, it's going up, below the xy plane, above, below, below. Pretty cool, huh? Let's do another one. Next one I want to look at. Okay, this one's pretty cool. This one, I look at, notice, x equals sine t, y equals sine t, and z equals square root of 2 cosine t. Now, notice, since x is sine t, your x coordinate can never exceed 1 or go below -1 because the sign is always between -1 and 1, right? And since y is sine t, again, y, the biggest y can get is 1 and -1. So if I look at my graph here, if I make 1 here, -1 here, I should make it to scale. That would be nice. Eraser's a little bit forgiving. And I let this be 1. And this be, and this be -1. My x's can't exceed -1, 1, and my y's can't exceed -1, 1. And also notice, since x equals sine t, y equals sine t, my goodness, the x's and y's are satisfy the equation y equals x. So let's see. My xy equations are going to be all along this line. And then, of course, it bats back there. But it can't go beyond here and here because x and y have to be between -1 and 1. All right, now lastly, though, I'm looking and I'm thinking, gee, well, what's the z's doing? Well, notice, since x equals sine t and z equals square root of 2 cosine t, all right? Since I know sine squared plus cosine squared equals 1, I can replace sine t with x, and since square root of 2 cosine t is z, I can replace cosine t with z over root 2, and that gives me x squared plus z squared over 2 is equal to 1. Who knows what that's the graph of in the xz plane? It's the graph of an ellipse. Remember we used that concept when we were doing ellipsoids? And the x is going to vary from -1 to 1. And notice the z is going to range from √2 to -√2. So if we just looked at what the x, z coordinates were satisfying, they're going to be satisfying this equation of an ellipse. Okay, so let me draw that ellipse on here. That was xz, huh? xz, an ellipse that went up to √1, up to √2, excuse me, down to 1, down to √2, and back. This was 1 here, so we got to make it go all the way around to there and back down there. So now we've got to be on this plane because we have to satisfy this equation y equals x. But since the x's and the z's have to satisfy this circle, think of dragging this circle along parallel to the y-axis or perpendicular to the x-axis. So as you can see, like at this point right here, okay, if you draw that over parallel, you would be here. All right, but this, so let's see if we can get this in. If you drag it along, since we have to satisfy y equals x, but the xz's have to satisfy this circle, notice what we're going to be getting here is a funny looking little ellipse, because the xz is going up to 1, down to -1, up to 1, but the xy's have to be going back and forth between this one and this one. Let's put this one on. Granted, this one was a little bit harder than the other ones, but let's put this on maple so you can see the picture a little bit. It's going to be sine of t. The y is sine of t. And the other one is square root, which is sqrt of 2 times cosine of t. And I'm just going to let t range from (0 to 4 pi would be fine. And again, this one you look at it first on maple and you go, what? I see nothing. Well, let's give it a little bit of an axis and let's just turn it a little bit. And look at that. It looks like a circle, but it's really it's an ellipse. An ellipse in 3-dimensional space. Okay, let's do another one. Oh no, I want to review a little bit. Find a vector representation and parametric representation for the line segment that joins this point to that point. By the way, those of you that print out my notes, I just put the parametric equation down the bottom for the notes because the vector's so easy to get after we get the parametric. Well, you know, people, we want to get a parametric representation for the line segment that joins this point to this point. It's the same as finding the equation of a line, which you just did on your test, right? The equation of a line is x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. All we have to do is figure out a point. X naught, y naught, z naught is a point that's on your line. Well, they gave me 2 of them, so you could use this one or you could use this one. I'm using this one for my x naught, y naught, z naught, so I'm going to use 3 for x naught, -2 for y naught, and I'm going to use 4 for z naught. Lastly, I need a vector a, b, c that's pointing me in the direction from p to q. So if I'm going from p to q, I'm going to subtract q minus p. So I'm going to go -2 minus 3 is -5. 3 minus a -2 is 5. And 2 minus 4 is a -2. So it's going to be, I should say, minus 5t plus 5t. And my c is a -2 minus 2t. Notice, when you let t be 0, these drop out and you get the point 3, -2, 4. When you let t be 1, you're going to get that point right there. Because 3 minus 5 is a -2, -2 plus 5 is 3. Of course, because you just did that subtraction. This is how much you're adding if t is 1. All right? And so this is the parametric representation. It looks just like the line, except you just let t range from 0 to 1, and it's going to take you from this point to that point as t ranges from 0 to 1. Now to do the vector representation, I didn't feel like gumming it up, putting all that stuff there. But the vector representation, you're just going to say r of t is equal to, and what's my x component? It's 3 minus 5t. What's my y component? Negative 2 plus 5t. What's my z component? 4 minus 2t. And that's my vector representation. So the two go hand in hand. They're not all that hard to do. But it's very important that, you know, if you got bummed out on the test and you didn't get your equations of your lines down too much, they're back. I mean, they're going to be back all semester. So you want to go back and make sure that you do have the equations of a line down cold, and that you don't have to look at your cheat sheet to get them either, because it's something that you will use all the time through this course. Okay. Find a vector representation for the circle x squared plus y squared equals 25. But before I do a vector representation, I want to do a parametric representation. Now this is something back from your Calc 2 days. Okay, it's not going to go, it hasn't gone away. Any suggestions? Since remember, cosine squared plus sine squared is equal to 1. All right, we can multiply through by 25 and make 25 cosine squared plus 25 sine squared to equal 25, or we can write this as 5 cosine t squared plus 5 sine t squared is equal to 25, right? And so I can let the x be 5 cosine t and let the y equal 5 sine t. And that's a wonderful parametric representation of a circle. Notice you might be saying, well, gee, why did she know to let the x be cosine and not the sine? Well, guess what, guys? It would have worked. If you had let x be 5 sine t and y be 5 cosine t, it's the same circle, except they're both going to start at different points and they might be going in a different orientation. Okay? But this is and now the vector representation, since it's just 2D, it would be r of t equals x component's 5 cosine t, y component is 5 sine t. And you probably remember this doing with your parametric equations. Now, I also could ask you to find a parametric representation of this ellipse. X squared over 25 plus y squared over 36 is equal to 1. Well, notice I could do this one by, watch this. I'm going to let this be x over 5 quantity squared plus y over 6 quantity squared equals 1. So I'm going to let this x over 5 be my cosine t, and this y over 6 be my sine t. And so if I let x over 5 be cosine t, and if I let y over 6 be sine t, I have a wonderful parametric representation. Notice if you take x over 5 as cosine t, that would give you x equals 5 cosine t, and y would be 6 sine t. And that's a very nice parametric representation of that ellipse. Notice what it's doing is it's letting your x range from -5 to 5. It's going from 5 to -5, and your z is going from 6 to -6. And what are you getting? This beautiful ellipse. Now the vector representation would be represented as, it's only two-dimensional because you just have an x and a y in there. So it would be r of t equals, the x would be 5 cosine t, and the y would be 6 sine t. It's the same thing. Okay? So it's important to realize that you can represent ellipses and circles parametrically. Now, what does that have to do with what we're doing in 3D? Find a vector function that represents the curve of intersection of these two surfaces. What's this the graph of? A cylinder. Well, in two-dimensional space, it's a circle, right? But in three-dimensional space, it's a cylinder, right? Right? This is a cylinder. What's this? A plane. Can you picture what a cylinder and a plane would intersect in? Think about if you've got a cylinder and you've got some plane coming down and slicing it, most likely It's going to be like an ellipse is what it's going to be, okay? But we have to come up with a vector representation. Now you look at this and you think, wow, this is really tough. I don't think I can do this. Well, let me show you how you can do it. It's not hard at all. What we're going to do is we're going to say, since I have x squared plus y squared equals 25, just looking at x squared plus y squared equals 25, I can get a wonderful parametric representation for that. What are we going to let x be? 5 cosine t. And we're going to let y be 5 sine t. Because notice, if you do x squared plus y squared, you'll get 25 cosine squared plus 25 sine squared, which is 25. So this is a wonderful parametric representation for the cylinder, for the xy. But now, our parametric representation has to also satisfy this equation? No problem. Since we have 2x plus 3y plus z equals 0, that tells me z equals minus 2x minus 3y, all right? So z would be minus 2, x is 5 cosine t, minus 3, y is 5 sine t. And so now I can say x is 5 cosine t, y is 5 sine t, and z would be, what do we have? Minus 10 cosine t, minus 15 sine t. Let's put this on maple and see if we are getting some kind of an ellipse. Okay, so what was it? It was 5 cosine t, bracket, 5 times cosine t, and the other one is 5 times sine t, so I can just put a 5 times there. And the last one's going to be a little bit of typing. It was negative 10 times cosine of t minus 15 times sine of t. And 0 to 4 pi is more than enough. Oh, why come nobody yelled out here? I made a typo here. Negative 10 times cosine of t. It wasn't able to read it because I didn't type it right. There we go. Does that look better now? Let's have it do it now. Oh boy, Mrs. Strocko is messing up a lot. She has double parentheses. Don't need that. Now let's try it. There you go. So as you can see, I mean, maple's very, and if we, as you can see, what do you have here? You have this wonderful little ellipse that you got when you sliced your cylinder. All right, just one more. No, I think 2 more from what I can feel here. Find a vector function that, I think, yeah, we have 2. 2, yeah, 2. Find a vector function that represents the curve of intersection of the two surfaces. Well, now, since y squared plus z squared is equal to 36, what do you think we're going to do? What am I going to do with that? Since y squared plus z squared is 36, how are we going to represent y and z parametrically? Again, notice, since sine squared plus cosine squared. Oh, okay, we'll come back here so we don't want to see maple now. We want to come back and see what I'm writing here. Okay. There you go. All right. We want to do the equation of y squared plus z squared equals 36 and x equals 2. Okay. So we have y squared plus z squared equals 36, and I'm just reminding you, since cosine squared plus sine squared is 1, it would be nice to multiply through by 36. And so I need 6 cosine t squared plus 6 sine t squared is equal to 36. So we can let our y be 6 cosine t, and we can let our z be 6 sine t. Okay? Did I say, might not have said the right things. Y is going to be this, and z is going to be this. So we're going to let y be 6 cosine t, and z be 6 sine t. Okay? And therefore, x is just 2. So we can let x be 2. And we're done. That was an easy one. And so looking at this, our vector valued function, r of t, would be 2, comma, 6 cosine t, comma, 6 sine t. And we're done. Okay, we have one more problem to do, which is far different than any other that we've done, so let's look at it. Last one that we want to do. Two particles travel along space curves. One is called r1 of t, is given by t squared, t cubed, and r2 of t is 1 plus 2t, comma 1 plus 6t, comma 1 plus 14t. And these are important questions. If I was using t for time, all right, I'm thinking about t being time, I could think of a particle moving along, and what this equation is telling me is where the particle's location is. Particle 1's location is according to the time on the clock. The same thing for particle 2. Now, there's two very particular questions. Do the particles collide, and do their paths intersect? Now, for the particles, just to give you an idea, I could have one particle moving along this curve and another particle coming along this curve. All right, and the paths are intersecting here and here. But in order for the particles to collide, I have to have particle 1 and particle 2 at the same point at the same time. You with me? You with me? So, in order to figure out, do they collide, in order to collide, their x, their y, and their z coordinates have to be identically equal to each other. All right, so in order for them to collide, the x coordinates have to be the same. So this x coordinate has to equal that x coordinate. T has to equal 1 plus 2t. That's setting the x's equal. The y's have to be equal. T squared has to equal 1 plus 6t. And at the same time, the z coordinates have to be equal. T cubed has to equal 1 plus 14t. So at the same time, their x, y, and z coordinates have to be identical. Well, if you're taking this equation right here, that would give me -1 is equal to t. And if I take -1 equal to t, I'm saying if t is equal to -1, yeah, the x coordinates are the same. Are the y coordinates equal? Well, the one on the left, -1 squared is 1. The one on the right is 1 plus 6 times a -1 is a -5. Are the y coordinates equal to each other? No. So do the particles collide? No. Because we don't have the x, y, and z coordinates all the same at one particular time. We force the x coordinates to be the same, but the y's are not, so it's not even worth our time looking at the z's. Okay, now in terms of do their paths intersect, the problem is the paths could intersect, but maybe for this particle it's at this point, maybe at t equals 3, and the other one might be here at t equals 5 at two different times. You with me? So what I'm going to do, since it could be different times, I can't use the same t for this particle as that particle because I can't make the x and the y coordinates equal at the same time. You with me? So I'm going to write r1 as t squared t cubed. But I'm going to write r2 as being on a different clock. How about 1 plus 2w, comma 1 plus 6w, comma 1 plus 14w. Now, in order for the paths to intersect, the x coordinates have to equal each other. T has to equal 1 plus 2w. That's the x's. The y's have to be equal to each other. T squared has to equal 1 plus 2w. And the z's have to be equal. T cubed has to equal 1 plus 14w. I go, oh my, that's 3 equations, 2 unknowns. Well, I'm not going to worry about that guy. I'm just going to worry about these two for starters. Since t has to be 1 plus 2w, in the second equation where I see t, I'm going to put in 1 plus 2w. Everybody with me? Oh, except I just messed up here. Where did I mess up? Does anybody see where I messed up? I just see I wrote something down wrong. We said, let's go back. In order for the two paths to collide, the x coordinates, the y coordinates, and the z coordinates must be equal. If the x coordinates are equal, t has to equal 1 plus tw. If the y coordinates are equal, this y coordinate, t squared, has to equal this y coordinate, which is 1 plus 6w. I should have had a 6 here. And then the z coordinates have to be equal. T cubed has to equal 1 plus 14w. So I have this equation right here. How am I going to solve that? Well, let's see. If I square out the 1 plus 2w, I would get 1 plus 4w plus 4w squared is equal to 1 plus 6w. Okay, and let's see, if the ones cancel, and I can subtract 6w, so I have 4w squared minus 2w is 0. Or if I factor out a 2w, 2w times 2w minus 1 is 0, so w is 0, or w is 1/2, right? Because 2w minus 1 is 0 when w is 1/2. Okay. All right, now notice, when w is 0, t is 1 plus 2w, right? So t would be 1 plus 0, which is 1. And notice when w is 1/2, t is 1 plus 2w, which would be 2 times 1/2 is 1. 1 plus 1 is 2. All right. Okay, so when w is 0, t is 1. Now let's go back up here. Okay, well, everybody have what I have there? Let's go back to the original equations. Notice, we just worried about making the x's and the y's the same. We didn't worry about the z's. But notice, when w is 0, notice we used w for this guy. We wrote him as 1 plus 2w, 1 plus 6w, and 1 plus 4w, because we had two different time clocks. Notice, when w is 0, R2 is where? R2 is at 1 plus 0, which is 1, 1 plus 6 times 0, which is 1, and 1 plus 4 times 0, which is 1. At the same time, at t equals 1, where is R1? R1 is at, plugging a t equals 1 into R1, 1 plus 1 plus 1. At two different times, they both go through the point 1, 1, 1. The paths intersect. Vice versa, we also had w equals 1/2 and t equals 2. Let's check that. If I let w be 1/2, R2 of 1/2 is the point. Now let's see. 2 times 1/2 is 1. 1 plus 1 is 2. 6 times 1/2 is 3. 3 plus 1 is 4. 4 times 1/2 is 2. Is that right? Oh, it's 14, excuse me. 14 times 1/2 is 7. 7 plus 1 is 8. And when t was 2, where is R1 at 2? Well, it was t squared, t cubed, so it's 2, 4, 8. So my paths intersect at 2 points. Now let me just make one comment here. When I actually did a set of simultaneous equations, taking this and plugging it in here and solving this and getting this, you with me? I didn't even worry about z. It's very possible that I could get two solutions here, but when I plug these w's and these t's into here, the z's would not be the same, and in which case the paths would not intersect. Okay, I just thought that would be an interesting one to do last. Is it by far the most important? No. What you people need to do now is, we're finished for today. Your homework, number 1, look over the book. The graphics are beautiful. So read pages 885 to 891, looking over at the examples. We did examples very similar, so you can just look over them. And then on pages 891 to 892, this is not a huge assignment. I want you to do 1 through 15, the odds, 34, 35, and 36. 34 and 36 on Blackboard, I have what those solutions are, because those are even answers. All right, so the even answers are posted with your homework assignment on Blackboard for you. Okay, see you next time.